All right, taking a look at Chapter 2, Section 4, Continuity. We have known this idea of continuous continuity, continuous functions for a very long time. Basic idea, and you've done this, is that you can draw the graph without picking up your pencil. Okay, so for instance, looking at this first graph, I've got 3 here that are all discontinuous. Okay, I can't draw this first one because if I draw this thing, I've got to pick up my pencil to go over that missing circle and then keep going. So it's discontinuous. Here I've got what's called a jump discontinuity, right? I'm here, I jump up, and I'm here. And here it's kind of a little bit of both. I've got this missing spot, it's called a hole, but it comes up here and then it keeps going. Okay, so these 3 things are not continuous, they are discontinuous. All right, but how do you describe this? Calculus, we want to be a little bit more rigorous in how we say something's discontinuous than not picking up your pencil. So 3 rules. All right. Step letter 1, number 1. Letter 1, what an idiot. Number 1, f of a must be defined. When you plug in a, you have to get an answer. So for instance, letter A here, you see how there's no black dot, there's no filled in circle. So that is why this one is discontinuous. All right. F of a, when I try to plug in a, I don't have an answer. Here, when I plug in a, I have an answer. Or when I plug in a, I have an answer. All right. Number 2, the limit has to exist. All right. So this was discontinuous from number 1. This one, the limit as we approach a, well, the limit as you approach from the left is here, from the right is here. This limit does not exist. So that's why this is discontinuous due to number 2. That limit does not exist. Number 3, the limit exists, and it's here, but the limit and the value aren't the same. The limit doesn't equal the value at a. All right, so all 3 of these things have to work in order for something to be continuous. Okay, and if it's not continuous, then it's discontinuous. All right, so let's just use that for these 3 problems. All right, using the definition, determine whether it's continuous at x equals 2. Well, step 1, can you plug in 2? If I plug in 2, it would be 4 minus 4 over 2 minus 2, 0 over 0. Well, f of 2 is undefined. So this thing is not continuous. All right, it fails step 1. All right, it's not defined. Number 2, let's check it out. If we plug in 3, negative of 3 squared, so that's negative 9 plus 4. It's equal to, so that's why I'm using that one. All right, so negative 9 plus 4 is negative 5. Great, so it does exist. It is defined at 3. All right, does the limit exist? Well, it's a piecewise function, so we have to do the limit as x approaches 3 from the left and 3 from the right. All right, as we approach from the left, that's when x is less than 3. We do get that same thing. That thing's continuous, like that piece is continuous of the piecewise function. It's a quadratic. So, that's going to be that same negative 5. But on the right side, when x is bigger than 3, if we try to plug in 3 here, because that's a linear equation, that's continuous, 4 times 3 is 12. 12 minus 8 is 4. All right, and there's our problem. The right side and the left side aren't the same, so not continuous. All right, our overall limit does not exist, so this thing is not continuous. All right, next up, let's see, it doesn't exist when x equals 0. Well, if we do f of 0, Well, x equals 0, we have the answer of 1. The limit as x approaches 0, well, we use this thing if x is anything besides 0. So we're looking at this equation, okay? And we've done that. The limit as sine of x over x, we have talked about. That answer is 1, okay? And finally, does the limit and the value, are those two things the same? Well, yes, they are. So yes, this is continuous. All right, so again, it has to pass all three rules in order for it to be continuous. We do have special names, and I talked about them. So we said this is removable, aka a hole, a jump discontinuity, and asymptotes would be an infinite discontinuity if you kind of have to cross over an asymptote for things to work. So one, I will say this is weird. One weird part is that certain functions can be continuous as long as we say when it's continuous, if that makes sense. So for instance, this first one that we have, we did that problem right here. We said it was not continuous because it's not defined at x equals 2. Okay. But if we just say, hey, it's good for all the numbers from negative infinity to positive 2, and it's good from all the numbers from 2 to infinity. So as long as we say, hey, it's continuous on its domain, if we don't look at 2, if we look everywhere else besides 2, if we conveniently leave that number out, then yes, it is continuous. All right, as long as you say over its domain and you state its domain, then usually they are continuous. Okay, it connects piece by piece for all those, and it connects piece by piece for all those, and it passes the limit rules and the evaluation rules for every other piece. All right, if you look everywhere besides that 2, you're good. All right, so as long as you know how to kind of work the problem, you can kind of say that some of those are in fact continuous. We don't do that very often. As long as you limit its domain, you can say it's continuous on this domain. All right, and then one very important idea that we do have that involves continuous functions is something called the intermediate value theorem. Okay, so as long as things are continuous, all right, the idea is that if I know a graph f of x is continuous, and I know it starts here and it starts here, and I know we have this height and I know we have that height, if my graph is continuous, if I want to find a height in the middle, I know it has to exist. Okay, so let me just kind of explain that one more time. If I have a function, I know it has this height here, and I know it has that height here. Well, that means if I pick any number, let's say this is at like 5 and this is at like 3, well, if the graph is continuous, then I know somewhere in the middle, somewhere in this zone, it has to also be a height of 4. Okay, whatever number's in the middle of those two, it's got to cross over all those things. Okay, continuous functions hits every number in between whatever values you have. Now, why is this important? Well, this is why this is important. If we have a function and we have this interval 0, 1, well, f of 0, if I plug in 0, 0 minus 0 minus 0 plus 1, that's 1. F of 1, 1 minus 1, that's 0, minus 3 plus 1, that's negative 2. You see how those y values go from positive to negative? Okay, so my graph was up here, now it's down here. Well, that was 0, 1. If I'm going to connect those two dots with a continuous function, it could do all sorts of weird things, but it has to cross the x-axis. I mean, it doesn't do weird things, but no matter what, to connect those two dots, you have to cross the x-axis. Meaning, yes, there has to be a 0, Remember doing that with polynomials all the time in Math 171? There must be a 0 somewhere in between 0 and 1. All right, that is what continuous functions can do for us. If we know it's continuous, we now know more things about it. Okay, all right. Could there be a 0 from 1 to 2? Well, we already know f of 1 is negative 2. If we plug in 2, that'd be what? 8 minus 4 minus 6 plus 1. 4 minus 6 is negative 2 plus 1 is negative 1. All right, so let's take just an idea of what our graph is. We were up here, we were down here, and now we're here. All right, so could there be a 0 somewhere in the meantime? Well, we knew there had to be one here, somewhere in this zone. What about from here to here? All right, between these 2 points, does there have to be one? No. But could there be one? Maybe. All right, I don't know if the graph comes up and comes down. If there's one, there would have to be 2, but there could easily be 0. Okay, I guess the intermediate value theorem just tells you if there definitely is one. It doesn't tell you that there definitely is not one. So I hope that makes sense. Okay, and then g of x equals 1 over x. Do we know there's a 0 between the interval negative 2 and positive 2? G of negative 2, 1 over negative 2 is negative 1/2. Right, so is there definitely a 0 in between those two? Well, I would imagine I'd have to connect them, and it feels like, yes, there would be. But then I take a look back at this equation. G of x equals 1 over x. What's the first rule of the intermediate value theorem? Continuous function. All right. Problem is 1 over x continuous? No, it's not. I can't do x equals 0. It's undefined. 1 over 0 doesn't work. So even though I have a negative number and a positive number in my y values, since the function's not continuous, I can't say that, yes, there has to be 0. The intermediate value theorem only works on continuous functions. Okay, so that is definitely higher level stuff here. The big things that we have to be able to do in calculus is confirm that something is continuous. Again, we need to hit all 3 of those ideas. It has to be defined. That's the most common issue. The limit has to exist. That's the second most common issue. And then the limit and the value have to be the same. All right, that's rare that they're not the same, but sometimes it happens. Usually if it exists, or if it's defined and it exists, most of the time, besides some random piecewise functions, sometimes those get a little weird. But if it exists and it's defined and the 2 things match, all right, then yes, it is continuous. All right, we love our continuous functions in calculus. Pretty much everything we do is going to kind of sort of start with this phrase, let f be a continuous function. And so it's going to be very, very valuable as we move forward.